This conference will now be recorded.
So today we'll be discussing diffraction of light, and Fraunhofer's diffraction we'll be discussing in detail. So we have already learned what is interference, and today we'll be learning diffraction of light. Before I give you the formal definition of diffraction, let me tell you something about diffraction today. See, in ray optics, what we have learned. In ray optics, we have learned light travels in a rectilinear path, right? What does it mean? If we do a simple experiment, suppose I keep a candle over here, okay? Candle, and you keep a cardboard making a hole at the center, okay? And keep another screen over here, okay? So you will see when the height of this hole is at the height of candle light, then only you will be able to see here the candle, okay? You can see the screen here, okay, when they are at similar height. If it is not, then you will not be able to see the candle light. So why is it so? It was because in ray optics we have learned that light can propagate only in a straight line path, straight path. So very good. So according to that notion, if suppose there is some obstacle in front of the source of the light, or anywhere in the path of propagation of light, suppose light is propagating like this. If suppose this light comes across some obstacle like this, so what it will do? Light will go in this way, okay, in this way, okay. Sorry, not like this. So what light will do? Leaving this particular region dark, leaving this particular region dark, light will pass like this, right? You will find bright region here according to our geometrical optics or ray optics. So there will be shadow over here. This is called the region of geometrical shadow. So this region is called geometrical shadow region. Here you will see darkness, and you look, if I say this is A prime, sorry, A, and this region is B. So this AB region you will be able to see light. Otherwise, here will be dark according to our geometrical optics. But what actually happens, the actual case is not the one ray optics says. Actually, what happens if I just take this as one obstacle AB, okay, and your light is coming like this. So you should get shadow over here. according to geometrical optics, what I had discussed just before 1 minute. But actually, what happens, actually, light gets bent at this particular region. Okay, and generally, light should, like, you should be seeing brightness over here, but you look what happens. Instead of being this part dark shadow, some light rays at the is here at the sharp edge. What will happen? Light will enters into the geometrical shadow region. Okay, and you will look here some light, at this particular region. Okay, I'll show you how it happens. Look, if I take this, is called aperture. Okay, aperture means small opening. So this is called aperture. See here, aperture is actually wide open, wide open. So when it is wide open, light almost goes straight line. You look, light almost goes straight line. Little bit of light you will see in the shadow region. Sorry, in this, so this here actually shadow region. In this case, this region will be shadow, but it is not exactly shadow because there will be some light getting into the region of shadow. This part you look, this part is getting into the shadow region, and because of that it will not be completely dark, rather there will be some light. But light means what? Will it be so bright? See, as you see here, it will be actually bright, but here it will be not that bright. What you will see, you'll see some dark bright, alternating dark and bright regions you will be able to see. Alternating dark and bright regions you will be able to see. And see, this is actually, so you can see the light is actually getting bent at the sharp edge of the obstacle. So this is obstacle. Look, you look, if this hole or opening or the aperture is very small, in that case, light will be bending like anything. And after bending, what will happen? Light will be diverging from that, diverging in all direction. You look, diverging, light is getting diverged. Okay, actually, according to geometrical optics, you should be able to see light only through this small opening. You should see some, if it is a round shaped hole or opening, you should see some round patch of light. But actually that doesn't have, and here you should be seeing dark shadow. According to geometrical optics, you should be seeing dark shadow. Okay, because this is, see, this is obstacle, but it doesn't happen. Actually nature is so clever. What it does, light gets bent. You look, light gets bent and get into the geometrical shadow region. See, this is the shadow region actually, geometrical shadow region, but you look, you will be able to see light over here. Okay, it will not be dark shadow, rather you will see some dark bright regions of light. Okay, alternating dark and bright light you will be able to see, dark and bright regions you will be able to see. And this is happening because of, because light is getting bent at the sharp edge. See, at this edge, see, this bending happens only when your aperture or the obstacle is very smaller in dimension. Suppose you use light of wavelength lambda, and suppose this has d opening, this width of this aperture is d, small d. So if the d is less than or equal to lambda, then this bending of light happens. Bending of light will be prominent. Okay, prominent. So this is called diffraction of light. So what is diffraction of light? It is the bending of light. Let us now see what you see, actually what you see due to this bending of light. Look, what you see is this. See, light gets bent, this look, and what you see is kind of this. You'll see alternating. Actually, in this shadow region only you will be able to see this. See, this is the opening. Anyway, you will see the whole light coming over here. But in the shadow region, you will see alternating. See, you will see first in the middle there will be a bright white patch of light, and then continuously decreasing bright and dark region. You will see. See, this is dark region and this is bright region. Dark, bright, like that. So it is actually a wide and most bright region, then alternately dark, bright, dark, bright, dark, bright. This kind of thing you will see. And if you plot the intensity with respect to various angle, see, this is the angles. So you will be able to see the intensity for the middle part will be maximum. So this is called central maxima, and then it is called minima, dark region. Then these are called secondary maxima. Secondary maxima. Okay, so this is diffraction of light, and because of diffraction of light, you will be able to see dark and bright region in the geometrical shadow region. Actually, you will be seeing here in this region. Okay, in this region, this particular pattern you will see in this shadow region. Okay, in this shadow region. All right. So look, if I give you formal definition, so it is stated as this: the phenomenon of bending of light around the sharp edge or corner of an obstacle or an aperture. So bending of light around the sharp edge or corner of obstacle. See, look here. This is the sharp edge or corner of this particular obstacle. So here light gets bent, like this it goes, like this it goes. Okay, this is the bending of light. You look, actually it should go like this, it should go like this, but light is getting bent. Obviously it will go in this way also, but some light will get into the geometrical shadow region. If you think this is theta, so this is the angle. Okay, so this, not only that, what is happening, not only getting into that, it is spreading. See, from this small hole or small aperture or small obstacle, the light is getting spreaded actually. See, light is getting spreaded like this, and then it will be like this, as I showed in the previous figure also. If I just come back with this figure, see here it is. So this is actually diffraction of light. Okay, so let us get the definition. So the phenomenon of bending of light around the sharp edge or corner of an obstacle and or an aperture, and its consequent spreading into the geometrical shadow region is called the diffraction of light. So this is the definition of diffraction of light. Now, there are different types of diffraction, different type of diffraction in the sense, so there are two prominent and famous scientists, physicists. One was Fresnel, another one is Fraunhofer. They had actually studied the diffraction phenomena with two different experimental setup, with with two different experimental setup. Different experimental setup. Sets up. Okay, sets up. So, and then according to their setup used, the pattern, diffraction patterns will be little bit different in shape and size, etc. So that's why there are two different types of diffraction. Experimentally we can see one is called Fresnel's diffraction, another one is called Fraunhofer diffraction. So what are the differences in the experimental setup? Let us see. See, in case of Fresnel's diffraction pattern or diffraction experiment, this is the slit or aperture, you can say. The source, you look source and the screen, they are kept at finite distance. So source here in this case, source and screen are placed placed at finite distance or closer to the slit, finite distance from the slit or obstacle, slit, from the slit. So in this case, what happens? Source is nearby this slit. So look, the source will actually, the light which is coming from the source will be in the form of spherical or cylindrical. So in this case, spherical or cylindrical wavefront will come and illuminate this slit. Spherical or cylindrical cylindrical wavefront will illuminate this slit. And since the wavefronts are cylindrical or spherical, they can be converged. They are, after diffraction, they will converge on the screen easily. Okay, they will be. So here, no lens is required. No lens required for getting the diffraction fringe patterns on the screen. Okay, they will naturally converge at the screen. But look, in the Fraunhofer diffraction, here the source as well as the screens are kept at infinite distance. At least the source you have to keep at infinite distance or at very, very long distance. So source, actually both source and screen, both are actually kept at infinite distance from the slit. Okay, and because of that, when your source is at infinity, what will be the shape of the wavefronts? So wavefronts which are coming from the source in, which is at infinity, so like this, it will be plane wavefront, plane wavefront. Okay, I'm writing WF is wavefront. So plane wavefront, you look here, plane wavefront, source at infinity. So when the plane wavefronts are coming and illuminating the slit, after diffraction, those plane waves actually remains plane wave, and it is necessary to have one convex lens, convex lens for which the screen is kept at the focus of the convex lens. So you have to use a convex lens, and you have to place the convex lens in such a way that your screen is at the focus of the convex lens. So this is how you will be able to see the diffraction pattern for Fraunhofer diffraction. You need to have a convex lens. After diffraction by the slits, the plane wavefronts will be almost plane. Okay, to converge them, you have to have one convex or converging lens. Okay, to see on the screen, diffraction pattern to see on the screen. Now one more point is, see, infinite distances, we don't know where we have to keep the plane source. So you know what is done in this also, source you can keep at finite distance itself if you do one thing. If you keep a convex lens here also, if you keep a convex lens just before the source, you keep a convex lens just before the source. How? The position of the source position has to be at the focus, principal focus of this particular lens. Then light after refraction, they will be parallel, right? They will be parallel. So parallel wavefront you will be able to get. So in fact, in Fraunhofer diffraction there are two lenses used, one just before the source and another one before the screen. Source, before source you keep because you want plane wave fronts, okay, or parallel rays or plane wave fronts. To get plane wave fronts you have to use a converging lens, and the source has to be kept at the focus of the converging lens, such that after refraction the light will be parallel, light rays will be parallel to the principal axis of the lens. And if you keep in the same parallel line to these slits, etc., then you will be able to get parallel wave fronts which will be illuminating this slit. Okay, so this is what is Fraunhofer diffraction. Okay, in Fraunhofer diffraction and Fresnel's diffraction, the diffraction patterns are of different shapes, and different theories are also involved in that. Now look, we in our syllabus will be discussing only Fraunhofer diffraction, and that to single slit. Single slit. See, in Young's double slit experiment we have seen there are two slits, S1 and S2. Fraunhofer diffraction also there are two slits, double slit and single slit as well. But in our syllabus only single slit is mentioned. So we'll be for the time being concentrating our discussion for the single slit. Okay, here you see in this experimental arrangement. So what we see, actually see, you have to keep a source over here, you keep a lens, okay, such that you get plane wave fronts as you can see from here. Okay, after diffraction, so this is Fraunhofer diffraction, source is at infinity, event screen as at infinity or at large distance from the slit. This is slit. Okay, this is slit. Look, these are the plane wave front, and these wave fronts are illuminating the slit. And after diffraction, see here, you know what happens in the slit. As you know, the slit is the opening, and at this, like, see, wave front is actually coming, plane wave front, and illuminating this, and each point on the wave front will be acting as actually a new source for secondary wavelets. Okay, each of them will be acting as source of secondary wavelets, and you know those secondary wavelets, they will interfere and give rise to diffraction pattern. So broadly diffraction is actually interference of light waves from the same wave fronts. Okay, same wave fronts. You look, in case of double slit, Young's double slit experiment, there are two sources. So waves were coming from two different sources. Here waves are actually coming from same source. In fact, same from the different points of the same wave front. Light waves in this single slit diffraction, you look, light waves are coming from various point sources from the same wave front, and they interfere. Okay, they interfere to get you diffraction pattern. Okay, so this is actually interference, nothing more than that. Okay, actually interference. All right, so what happens? So after interfering those secondary wavelets, so they will create, see, you know already the interference creates alternating dark and bright fringes. Okay, the same thing you will be able to see over here. Okay, so what you see exactly, as I have shown you in the very beginning, look, you will get a very white patch at the central point of the screen. So this is the screen. You look, this is the pattern you will be able to see. If you take a laser light, if you take a laser light over here, laser light, okay, and you just take a cardboard and just have a very narrow slit. In fact, you can just take a blade and just scratch it like this, okay? Okay, cut it with the blade once, that's all. And you pass light from laser. So you will be able to see at the screen at large distance, you will be able to see a wide bright patch like this, and then darkness. Some places there will be darkness like this, and then again you will see bright. But see, this is so wide. This bright patches will be having lesser wide width. Okay, lesser and lesser. Actually, you'll get uh, increasingly lesser or decreasing, so decreasing width of this. And not only that, intensity also, you look here, the intensity is this much. First maxima, this is actually first secondary maxima. Secondary, these are called secondary maxima, and this is called principal maxima or central maxima. As you can see, you can see that. So this is called central or principal maxima. Principal principal maxima. Principal maxima. And others are called, see, these maxima, these are also maxima only. Here you will see brightness, like you can see here, brightness. And in between brightness, you will get darkness. See, this is a central bright, and before first, secondary, this is secondary, first secondary maxima. Secondary maxima. Why secondary? Because it is not intense as the principal maxima. We'll see why it is so. So, and width also, you look, this is the width. Here, this is the width, angular width. So this width will be continuously decreasing, and sometime you will not be able to see anything. At very large distance, you will see nothing. Okay? So these are called secondary maxima. Okay? Their intensity as well as width will be decreasing continuously as you go further and further. So these are called order of the fringes. First, second, third. These are the first order secondary maxima, then second order secondary maxima, third order secondary maxima, like this. And these are actually first order minima. This is second order minima. Okay, first order. This is actually first order minima, second order minima, third order, first, second. Okay, dark are called minima. Dark regions are called minima. This will be fourth minima. Okay, like that. So this is how you see a central bright fringe. This is bright. Obviously, you can see this central bright fringe, and on either side of this central bright fringe, you will see alternatingly bright, dark, bright, dark fringes. Okay. So this is actually Fraunhofer diffraction. Okay, this is Fraunhofer single slit diffraction. So diffraction at single slit. Now you might be thinking, sir, how you analyze that there will be minima over here, there will be maxima at this particular position, again minima, again maxima, again minima, again maxima. How do you analyze that? How to get this? And one more thing is how this central maxima has got this much intensity and this much wide. Why is it so? We'll discuss. So this is our main agenda in this Fraunhofer diffraction, to find out the position of the secondary maxima, position of the minima. So position of the minima. So these are actually angular position. Obviously, you can see. So this is actually, this is angular the angular position. Okay, if you draw this, so this is theta 1, theta 2, like that. These are the angular position. So what are the angular positions of various maxima, secondary maxima, and position of minima? How to find out? In fact, we will be learning what are the conditions for like see in Young's double slit experiment we have seen what are the conditions for conditions for constructive constructive and destructive interference, right? Similarly here we will be learning what are the conditions for minima, diffraction minima, and what are the conditions for diffraction maxima, secondary maxima, and from there we will be able to find out the positions as well as width of width of each central maxima. We can find out what is the width of central maxima, then other secondary maxima and minima as well we can find out. So this is our main purpose or aim of the class today. So Deepa, so far whatever I am discussing I have discussed already. So do you follow? Do you follow? Are you able to understand? If not, you can ask me anytime. Okay, we'll go to the next topic. Let us see. See, condition for central maxima. Condition for central maxima. So central maxima has got maximum intensity, maximum width. Let us see how do we get maximum intensity. So that much intensity, how do you get? Look, so this is the central maxima here, the same figure again shown. We'll find out the reason for that. See, I have just see this is the magnified figure of the slit. Okay, magnified figure of the slit. Look, slit has, suppose it has, actually let us say this let us take as A. Width of the slit let us take as A. Okay, let us take this as A. So see there are, if you just see any so like see this, there will be a plane wavefront over here, and since the parallel rays are there, so each point, look, this point, these points on the slits, they will be acting as source for the secondary wavelets. And look what happens. What happens? So the light, see, or wave fronts which are actually emanating from this each point, when the meet at the central point on the screen, like this place, okay, O, suppose this is O. So when they meet, all of them actually have the same path difference. See, whenever I say maxima or minima, so there will be involving, see, this diffraction is nothing but interference. So there will be interference. So interference in the sense you can find out what is the phase difference, path difference, and according to that, you can find out the condition for maxima and minima. Okay, where the constructive interference happens, that will be maxima. There will be maxima. Where destructive interference happens, that will be position for minima. Okay, so we have to see the path difference of the lights interfering. Suppose this is the central point D or O, sorry, do O, central point O, okay, central point O on the screen. Look here, this is O. So it is actually just on the perpendicular bisector of the slit itself. Look, this screen, see O point, which is the middle point of the screen, is exactly on the perpendicular bisector. So if light comes now after diffraction, they meet at O position, wherever your slit position may be, wherever your source position may be. See, when they meet at the middle point of the screen, okay, middle point of the screen, they actually don't have any path difference. Look, this path, if I say this is B, and this is A, and this is O. So path AO, sorry, AO is equal to BO. Okay, if I take another point over here, another point over here, so they also actually meet like this. So these two sources also have the same path difference. So this light and this light has the same path difference. Okay, so whatever light comes from any point on the slit, all of them will meet at O, and at the O point, all the lights which are meeting or interfering, they will not have any phase difference. If there is no phase difference, phi is equal to 0. So condition for this is phi is equal to 0. Phase difference 0, then any pi, 2 pi, 3 pi, 4 pi. This we have learned. This is a condition for bright fringe or constructive interference. So you'll see bright region. And why this matter wide? Because everywhere on the slit will send light to this point. Okay, so and they will actually meet like here, then one light from here, one light from here, one light from here, like that. Okay, they will meet in the middle region. Actually, in the middle region, the light goes from each point on the slit. Each point on the slit will have the same path difference, as you can see from here. See, they have same path difference. All of them have the same path difference when they reach at the middle portion of the screen. So that's why there will be constructive interference, constructive interference. Okay, and this constructive interference will give you the brightness over here. Okay, and why is this much wide? Because the whole slit will send light to this place. So that's why the intensity also will be more. So intensity will be maximum, width of the central maxima will be maximum over here. Okay, so this is actually the reason for having highest intensity at this particular position. Highest intensity, highest intensity at this particular position. This is called central maxima or principal maxima. Okay, now we'll go and see where the first minima would happen. See, these are the minima. On either side there will be dark and bright regions. So the first dark will be the first. So this is called minima. This is called minima. Dark regions are called minima. So this is first minima. Okay, this is first minima. Here in this direction, this is the first minima. Okay, then it will be second minima, third minima, fourth minima. Okay, so each of the actually in these places, all these places actually, the destructive interference will happen at this particular region. But we have to see how we can explain that there will be destructive interference, or there will be there will be rays reaching out there with 180-degree out of phase. Okay, so let us see now position of diffraction minima. Position, actually if I find out the condition, then we will get the position of the first minima from there. So look, to find out the first minima, before I go for first minima, let us do one thing. Let me discuss this particular figure. So I am here, according to your textbook, I'll just take the slit width according to textbook. It is taken as A. That means the length of AB is A. Okay, this generally has to be some millimeter or maybe more than, less than that. Okay, some millimeter, 10 millimeter, 5 millimeter, or more than, even less than that. Sometimes extra motor also. In different cases, it is different. Okay, so this is the, and the light used here has wavelength. Light used has wavelength lambda. Okay, lambda. And see, source to slit to screen distance is d. Okay, and this d is actually much greater than your lambda, and also this slit width. These are few assumptions we are taking. Okay, and if this is the case, so the let us see, we have to find out the position of diffraction minima. So we are thinking that light from A and B, when they meet at position P1, at the position P1 they will give you minima. That means, here will be deep like this. Okay, so these are the two positions of minima. Okay, this is central maxima, as you see here. This is the minima. This position, let us say, this is the particular position where the minima is happening, and how it happens minima, we have to discuss that. Okay, let us say this point is at theta degree angle with respect to the this one. So C and C is the middle point, perpendicular bisector P0. Okay, CP0. With respect to CP0, this elevation angular position is theta. And since D is taken as very large than this and this, like slit width and wavelength, we can think that all the rays which are going from, like, each point of C is the middle point, and then A, from all these points, when they are meeting at P1, they actually interfere out of phase. Okay, they interfere out of phase, 180 degree out of phase. That is what I'm just assuming now. Okay, and look, if you want to really find out condition, what you have to do, you have to find out the path difference between the lights. So I'm just taking two lights first. See, the light which is going from A to P1, and the light which is going from B to P1. These two lights if I take. So we have to find out, let us see, we have to find out the path, the distance of the path they travel. Okay, the difference between them we have to find out. So actually here, to find out this, you have to draw a perpendicular from A to this BP1 line. I'll draw it actually here. Look. So ray is going like this, and another ray is like this. So this is the P1 point over here. This is the P1 point. Okay. And see, this is your A, this is B. Okay, I'm just taking the perpendicular bisector, or the middle point is this, as P0, as you see here in the screen. Now this is actually BP1, this is suppose C is the middle point. So you have to find out what is the path difference, path length AP1. Like, you can find out the difference at a time. So this difference you have to find out what is the value. So to do that, you look, if I just draw a perpendicular over here, which is D, AD. Okay, so this is the anyway slit which has with A. That means AB is A. Okay, so look again, we have seen these rays are actually having angle. This angle is theta. If you look here, okay, okay, so this point is theta. Okay, so this is theta. Okay, theta angle. Both the rays are at theta angle with respect to this perpendicular bisector, or horizontal, with respect to horizontal. So that is how you see in this figure properly. So I'm just, what is trying to do is, let us actually draw it again. This point was okay, so this was not okay. So this is also theta, and this is also theta, this particular angle. So we have to find out, so this BP minus AP, look, this is actually nothing but BD. This much is the difference. Look why it is so. See, if I say this is D, this particular point is D. So DP1, P1 and AP1 are of same length. AP1 is equal to DP1. They are of same length. Okay, only thing is this much is the difference. So BD, this much length if I find out, so then my things are done. Okay, look at this particular position, you look, this angle is theta. Okay, and look, this is actually with this is 90 degree. Here it is 90 degree. Okay, I'll just remove this and show you. See, this particular angle is 90 degree. I'm showing this one. This angle is 90 degree, isn't it? 90 degree. Okay. Then what is the angle? What is the angle? This particular angle, let us say this. If I just take this triangle A, D, and B. Okay. So this angle ABD angle, this angle will be, this is theta anyway we have learnt. So this is 90 minus theta. Okay. This particular angle will be 90 degree minus theta. I'll write outside. So this particular angle will be 90 degree minus theta. Okay. And this is, since this AD is perpendicular, this is anyway, it is 90 degree. This is 90 degree already, you know. So what will be this angle then? So total will be 180. So you write this total will be 180. So 90 goes, you know, you look, if I say this is X, this particular angle is X, BAD, that particular angle is X, then X is equal to theta. Okay. So what we have developed here is, see, this particular angle, this particular angle, this particular angle also will be theta. Okay. So, all right, I'll just clean everything. See, I'll write AB has length L. So light wavelength we have taken lambda, and see, D the screen distance from the source. This is much greater than these two. These are the things we had. So what we have got. So this particular angle is theta again. Okay. So from here you can easily find out. So this is A. So let me just draw one thing. Draw this. Uh, okay. So this is the condition here. Okay, this is theta. Okay, and this is the A, this is B, this is D, and this much we know A. So we can find out what is this BD. BD will be actually, see, this is perpendicular, let us say this is actually hypotenuse. So BD by hypotenuse is A is equal to sine theta. So BD will be A sine theta. So we got the path difference between these two lines. Okay, path difference. If they meet at P1, then this BD, this length is actually A sine theta. Okay, A sine theta. Okay, and see, let us say, let us say P1 point will be dark if the path difference between the two lights, path difference is lambda. That means what? That means what? A sine theta is equal to lambda. A sine theta is equal to lambda. This is the condition we have got. But how to justify that? At this condition here, it will be destructive interference. How to justify that? So what we have seen, what we have done here, we have found out the path difference between the lights, extreme two beams, extreme two light from the slits. See, A from A point, from B point. When they meet at P1, we are just thinking that there will be dark fringe or darkness. There will be minima, first minima. That is first minima over there. Minima means on like darkness, and minima to happen you should have two lights interfere destructively. Now look, we have taken this A sine theta is equal to lambda. A sin theta is equal to lambda is the condition for this P1 to be dark. Why this condition is satisfying this P1 to be dark, we will now justify. Okay, so what we have seen, the light which are actually coming from extreme 2 points A and B, what will be the path difference in terms of lambda? This will be single lambda. Path difference is single lambda. Now look, we have to actually see, we have got the condition like this. We have assumed that when the path difference becomes equal to lambda, then P1 will be dark. But why is it justified? Is it justified? We'll justify that. How you get? Look here. Uh, we have got already the path difference, let us say delta. Here actually they have, okay, so this is suppose A, so this will be A sin theta, what we have already discussed. Okay, so delta L here, path difference is A sin theta. Okay, this is the thing here we have got already. So look what happens here, this is A and this is B, this is B. We have to show why at P there will be darkness. Okay, that is my concern. Look, if I divide this, divide into two equal part, divide into two equal parts. Divide the slit into two equal parts. Okay, slit. So it was, see, if this is the C middle point, as you see from here, it will be A by 2, like, and this will be A by 2. There are two parts now. Look, then if light goes from this particular point to P1 and from C to P1, what will be the path difference here now? What will be the path difference? Earlier, from light, when it is going from one from P, like this particular point A, and another from B, the path difference was lambda. Now you have got two equal parts. That means, see, you have divided into two. Like, see, this will be corresponding. See, if a light go from here and another from C point, the path difference will be lambda by 2. I hope you will be agree. Like, you will be agreeing with me. See, now this point is C. Now, if a light goes from C and another light goes from B, they also meet with path difference lambda by 2. Okay, path difference lambda by 2, right? Look, I'll just tell you one more thing. So if we think that the light which is going from A and B, they have path difference lambda when they meet at P1. Now I have divided that slit into two parts. So this is AC and CB equal part. Now if a light goes from A to P1 and another light goes from C to P1, what will be the path difference? Lambda by 2. Okay, if any source, this one C, okay, like C, now a light goes from C and B, they also will have path difference lambda by 2. Okay, because these are from half portions, not the full portions. Okay, not only that, if I divide this into various small equal parts, suppose if I just divide into 10 parts, if I see, suppose 1 2 3 4 5 6, suppose 6 parts, if I divide into 6 equal part, 6 equal part means lambda by 6, you will get actually lambda by 6 each part. Okay, If I divide it into two parts, you will get lambda by 2 for each part. So light goes from this, and this will give you lambda by 2 path difference. Okay. If suppose I take I take one more source here, not at the extreme A point, some point in the middle, then corresponding point in the lower part, which is exactly in the middle again in the CB part, will give you path difference lambda by 2. Okay, I hope you are understanding. Suppose I have a slit, okay, so of some 10 centimeter, or maybe some, let us say, yeah, 10 centimeter. Okay, I just break into equal parts. See, when light goes from this 10 centimeter, this slit, you get lambda path difference. Now if I just make into 5, so this side is 5 centimeter, okay, and this side also 5 centimeter, okay, 5 centimeter. So if light goes from now one from here and another from this part, this will obviously give you lambda by 2 path difference. If I take from this particular point and this point, this will give again lambda by path difference. If lambda by 2 is the path difference, so what will be the phase difference? Phase difference will be 2 pi by lambda into lambda by 2. 2 goes off, and see what you get phase difference. 2 pi by lambda, and you get path difference lambda by 2. So lambda goes, so you will get actually pi. Uh, so you should get odd pi. So 0 pi, 2 pi, 3 pi. This will be constructive interference, but let us say this is okay. So lambda by lambda by 2 means, actually, see, this has to be even pi. Okay, 0, 2 pi, 4 pi will give you constructive interference. Okay, and when you have odd pi's, okay, pi, 3 pi, 5 pi, 7 pi, then you get destructive interference. Okay, I hope you are understanding from the concept of interference. So the destructive interference will happen here. Okay, Deepa, I'll take another 5 minutes maybe to this like conclude this. Just be with me, because this is a elaborate topic. If I have to again take the class on the same topic, then I have to start from beginning. Okay, better you just be with me for some five maybe maximum 10 minutes. We'll finish this part. So you look here, when you break into two parts, then you get actually lambda by 2 path difference between the lights. See, if you think, sir, you are taking only light from here and middle point, so why don't you take light from here? Yeah, I'll take light from here. See, if I take just exactly middle of AC, middle of AC, then here, from here light goes to P1, and you take another light from this middle point of BC, CB, they will actually interfere out of phase. They will give you lambda by 2 path difference. Okay, if you just take 3/3 of this, then you have to take again from here. So look, if you just have, that means, you can have sources in the first half of the slit. Okay, for which, for like sources, for each of them, that means whatever source you take in between this, for each of them there will be a corresponding source in the CB part. Okay, each of them, for each of them, there will be a corresponding source. There will be a corresponding source, which will send light with path difference lambda by 2. Okay, I hope it is clear to you. Okay, so suppose I have 10 sources like that, 10 sources. So like that, if you have 10 slits like that, so suppose you take first, then ninth one you will give you lambda by 2. Okay, like that. 8 you take, then 2 second and 8 they will give you lambda by 2. Like that, there will be whatever source you pick up over here in between AC, there will be a corresponding source between BC which will send a light which will interfere at P1 180 degree out of phase. Okay, and thus they will actually give destructive interference. Okay, similarly if you just break into, see, if you want to see the second minima, this is first minima, second minima. So condition for this second minima, okay, look this. What is the condition we get then? A sin theta is equal to lambda. This is the condition for getting minimum. So this is the condition for diffraction minima. Condition. If you want to see the nth one, then theta n is equal to n lambda, plus or minus both side you will see. So this side suppose plus lambda, then plus 2 lambda, okay, then 3 lambda, like that you will be able to see. Okay, and see this is the condition for diffraction minima. Okay, I'll just clean this and write. Okay, so what is the condition for diffraction minima? A sin theta n is equal to n lambda with a plus minus sign, and since this d we have taken much larger than lambda and a, or the slit with a here. Okay, so this sin theta or tan theta, since theta is very small, then in this case actually at this condition theta will be more small. Theta is very small. If theta is very small, sin theta tan theta will be equal to theta. So a theta n is equal to plus minus n lambda. That means this is the condition, this is the position for angular position for n dark fringe n lambda by a. Okay, so if you just put theta is equal to 1, so look, this is theta 1, suppose this is theta 1, then theta 2, like that you will find out theta 2 position over here. So theta 1 is actually having angular position lambda by a. Theta 2 you will have 2 lambda by obviously both sides, so here will be minima over here also p1 prime. Okay, and this will be 2 lambda by a. Okay, like that. All right. Okay, so how to get the condition for secondary maxima? Secondary maxima means this one. Okay, so secondary maxima, see, you will get minima over here, right? Like this. Here minima, p1 prime here suppose, and this will be minima. This is again maxima here. So this position, how do you find out? See, this is actually at lambda by a distance. So path difference was how much? Lambda over here. So obviously this has to be greater than lambda. Greater than lambda. Path difference has to be greater than lambda. But we don't know exactly what is the lambda. But for the timing, let us say the secondary maxima occurs when path difference a sin theta, we have already found out a sin theta path difference becomes 3 lambda by 2. Okay, I'll just, so path difference which we have already calculated, so that will be 3 lambda by 2. So that is the condition. Suppose there will be secondary maxima. So a sin theta is equal to 3 lambda by 2. This is the first maxima, first secondary maxima. What is secondary maxima? I'll just go back and show you. See, this is the first secondary maxima, this one. Secondary maxima. We have to find out the condition for this maximas. So we have found out the condition for minima. What are those? Theta n is equal to plus or minus n lambda by a, or a sine theta n is equal to plus or minus n lambda. So this is the condition for minima to occur. Now we have to find out the same thing for like position for secondary, first secondary maxima. Let us say it is happening at the path difference 3 lambda by 2. So to explain that, let us do one thing. Let us break this slit. Okay, divide the slit. Okay, A into three equal parts. Okay, three equal parts. Equal parts. Three equal parts means, see, point A and this point is B. The whole part was giving path difference how much? This was giving path difference lambda. If I break into small parts, suppose this is A, B, and then C, and another one is D here. Okay. So you look, this part is now lambda by 2. This part is lambda by 2, and this part is lambda by 2. Now AB is actually giving you how much? 3 lambda by 2 path difference. I am saying that first secondary maxima will occur if the path difference between the lights which are interfering at particular position is 3 lambda by 2. There you will get first secondary maxima. So 3 lambda by 2, that means the light which are going from A and B will give you 3 lambda by 2. Now what I have done, I have divided this A and B into three equal part. Look, 1 and this 2. So then this part will give you, so total was 3 lambda by 2. So this will give you 3 lambda by 2. Again this part will give you lambda by 2, and this particular portion will give you lambda by 2 path difference. That means if light goes from here, they will give you lambda by 2 path difference. If one light go from here and another goes from here, so they will also give you lambda by 2 path difference. Similarly, if goes from these 2 points, they all they will actually interfere with lambda by 2 path difference. So lambda by 2 path difference means they will give you destructive interference. Okay, all right. So look what happens in this case. In this case, what happens? See, this particular part, first part, this is second part, and this part is third part. So you look, we have seen the condition was if the path difference is lambda, then destructive interference will happen. Destructive interference will happen, and there you will get like destructive interference because if the path difference is lambda. Now you look, any source from here and here will give you lambda by lambda by 2 path difference, that is fine. But if you take any source in between two, see, in between these two, if you take this light and from here another light, they will give you lambda path difference. Okay, because this part is lambda by 2. Okay, and this part is also again lambda by 2. This part is lambda by 2, second part is lambda by 2. So if light goes from this, okay, this suppose A point, this is C point, this is B point, and this is D point. So light from A and D, they will give you lambda path difference. They will interfere destructively. So give nothing, no light, no brightness will be happening. Again, if you take any source here, corresponding point will be there in this, in between this. So that will give you. So if I take a number, maybe you will be able to find out. So suppose I have some 15, so like 15 sources which will give you 3 by 2 lambda. Okay, like this much path difference it gives. If I just break into three part, 5 5 5, so there are 5 sources here which gives lambda by 2. Again you have, suppose this part, 5 sources. So here 1 2 3 4 5, like that, and here 6 7 8 9 10, like that, and then 1 2 3 4 5 5 5. Okay, so 5 5 and 5 sources are there. So look, first 10 sources they will give, actually if you just take the first one, and then the 10th one, they will give you path difference lambda. If you take the second source from this particular first portion and you take 2, means you have to take again here there are, oh, sorry, there are, yes, so you take the 12th one, that will give you path difference lambda. So this is how they will give. So each of them actually will give you path difference lambda. It will be 11th maybe. Yeah. So this is how. So in between these two portions, there will be sources, corresponding sources, which will give you path difference lambda or destructive interference. That means whatever light goes from these two particular portion division, they will give nothing they will give. And see the remaining lambda by 2 portion, this particular portion, third half, that means, see, you have lambda by 3, sorry, lambda by 2, and then this is lambda, and this is actually 3 lambda by 2. This portion, the last division, this particular portion will send light as it will go. Okay, it is going to particular position. There will be no light from other places which will actually interfere out of phase, okay, or will give path difference lambda. That will not be there. So these two particular portion, they will send light which will be interfering out of phase, 180-degree out of phase. Okay, only this particular portion will be no destructive, there will be no destructive or destructive interference. Okay, so this light will give you some brightness. So this is how you will get brightness due to the third portion of the slits. Okay, third portion. That means, you have, as I showed, if there are 15 sources, you get nothing from first 10 sources. You get light from only 5 sources. That's why intensity becomes very less. That's why intensity becomes less. Okay, so that's how you get, see, that's how you get, see, that's how you get the first maxima, where 3 lambda by 2 path difference, when 3 lambda by 2 happens. Okay, similarly, if you just take 5 lambda by 2, then you have to divide the slit into 5 parts. Okay, one, so 2a by 5, then 3a by 5, like that. You have to divide into 5 parts. Then 5 parts means like this, 5 equal parts, 1 2 3 4, another part is this. So first 4 part, they will actually give you destructive interference, destructive. Okay, only this remaining part will give you light. Okay, so if the path difference is 5 lambda by 2, similarly, if you take path difference 7 lambda by 2, 7 lambda by 2, you have to divide these sources into 7 equal parts. So 6 parts will actually interfere destructively, only 7th part will give you some light. Okay, so that's how secondary maxima happens. At, if we just go for the general formula, for nth secondary maxima, you have, see, 2n odd lambda by 2, right? 2n plus 1 into lambda by 2, odd lambda by 2. If you just divide this, obviously there will be plus minus, both side you will see the same thing. So if you just divide with the 2, so n plus half into lambda. Okay, if this theta is very small, we'll just take the approximation. So it will be nearly this, theta n will be n plus half into lambda by a. Okay, so this is the condition for secondary maxima to happen. Condition for secondary maxima. Okay, secondary maxima. All right, so you can see if I plot the intensity pattern, it is already plotted over here, or maybe in your book also you can see that. See, this is actually, see at lambda, this is actually lambda by A, this is minus lambda by A, then 2 lambda by A. Here also this will be 2 lambda by A position for the uh, second minima, okay, like that. And this will be, first minima will be at 3 lambda by 2, this is 3 lambda by 2, and this is again 2 lambda by, okay, 3 lambda, 3 by 2, 3 by 2 into lambda, like 3 lambda by 2a, like that. Okay, then the second, this one will be at 5 lambda by 2a. Okay, then the other third one will be at 7 lambda by 2a position. So these are the angular positions. Okay, these are angular positions. So now you have to find out what is the width of the central maxima. Width of the central maxima we will find out here. See, we have got theta for this particular position. This is the dark one. So theta, first dark, we have got lambda by a. Okay, and here we have got minus lambda by a. So what will be the angular width, angular width of central maxima or principal maxima? That is 2 theta. 2 theta means you get 2 lambda by a. So this is the central, the width of the central maxima. Now if you want to know what is the position of this minima, first minima, what is the position, then you have to find out x. Suppose this is the x from, so here starting from 0. So x, how to find out? You look, this is theta, so this is suppose perpendicular, so you can find out tan theta is equal to perpendicular by d. Okay, so tan theta can be written as theta. So for the first minima you get x1 is equal to d into theta. So theta was how much? Theta was lambda by a. So you get d lambda by a. D lambda by a. You get the position. So this is the linear position and this is the angular position, angular width. Okay, so yeah, so this is the thing. Okay, so with this I'll stop the class. It was a long class, but anyway I had to finish this in a single class. Deepa, I'll not bother you today again. If you have, you just read this part. If you have any doubt, you can ask me on the next day on the diffraction part, because this is very, very important and very good concept is there in this particular topic. So if you have any doubt, you can ask me on the next class. Okay, so today I'll stop it here.
Thank you, sir.
Okay, Deepa. Okay, bye for today. Okay.